I think we've done enough differentiation up until this point. We're, 14 or so episodes in. So it's time to switch our focus to the opposite of differentiation, integration. Now, let me warn you, integration is generally considered the harder of the two, the more developed of the two, but also the more useful of the two. And as you'll see as we go ahead and start exploring different integration techniques, you'll see how it becomes, well, let's just say I'm not sure this whiteboard is quite big enough, but for now, we can start off pretty simple. So as I said, integration is the opposite of differentiation. You take a times, to get rid of it, you divide. You take a plus, to get rid of it, you minus. You take something that's been differentiated, and to get rid of it, to get it back into its original form, you integrate it. So it is the opposite. So, my x squared function, for example, if I differentiate this, so d by dx of x squared is equal to 2x. Which means if I want to go from 2x to x squared, I need to integrate. Now, the way I write this is as follows. The integral, this is the integral sign, kind of like a really long S, but with a very straight bit in the middle, of 2x dx is equal to x squared. Okay, so these two would be opposites of one another. Now, just a little bit on the notation. We signal that we're beginning an integral by using the integration sign, this big S. This tells us that we are starting the integration. We then include the function that we are integrating, so in this case 2x, and then we add I kind of call it a variable qualifier, just letting us know what variable we are dealing with. The same way up here, I write d by dx to let me know that I am only interested in the x variable. Anything else, a, y, lambda, whatever, isn't going to be used. I need to add that here as well. It also kind of serves as a cutoff. After the dx, anything else is no longer included in the integral. The dx is the end of the integral. It's kind of like brackets on either side. Okay, so this is how we would write it, but how do we actually calculate it? How do we go from the integral of 2x to x squared? Well, there's no real simple way of doing it like we have with differentiation and first principles, and that's because it's a tad bit more complicated. So a differential, we know, is the gradient of a curve. Here's my curve. If I want to find the gradient, the rate of change at any point on this curve, I differentiate it. But an integral does something else. An integral gives us the area underneath a curve between two set points. More on that in the next video. So when it comes down to coming up with a mathematical model to, not simplify it, but explain it from first principles, it's a bit difficult. There are things like trapezium rules that we'll cover later on, and things like, just simply counting squares underneath a graph to get an area, but there isn't really a first principles. So the first way that I'm going to introduce integration is just by the polynomial method. So the same way with differentiation, if I want to go from x squared to 2x, rather than bothering with all of the first principles rubbish, I simply state I've got a squared up here, I'm going to bring it down in front of the x, so I get a 2x, and then I'm going to minus 1 from the power, and I get 2 minus 1 is 1, 2x to the 1. Well, let's do the opposite. Let's start with the 2x and work backwards. So what was the first thing that I did here? Well, let's make a kind of a list. First thing I did was times by the power, then I minused 1 from the power. So, to integrate, I need to work backwards and also in reverse. So instead of minusing 1 from the power, I'm going to start with that and I'm going to add 1 to the power. So I've got 2x to the power of 1, so that's going to become 2x squared. And then, instead of dividing by the power, instead of timesing by the power, I'm going to divide by the power. So I've got my new power. I'm now going to divide the entire thing by that new power. The 2 and the 2 cancels, and I'm left with x squared. The exact opposite way that we did differentiation. Instead of timesing by the power and then minusing 1 from the power, we work backwards and opposite. So we add 1 to the power and then divide everything by that new power. And remember, you can always just differentiate everything to check that we are correct. Okay, let's have a look at this polynomial here. Perhaps maybe it's a graph. 2x squared plus 5x plus 1. How do I integrate that? Well, opposite of differentiation, but still the same kind of principles. I can still just integrate each term individually and end up with the correct answer. So 2x squared, well, let's work backwards. Let's add 1 to the power, so x to the power of 3. Then let's divide the entire thing by that power. So my 2x cubed, and I'm going to divide by 3. Next one, let's add 1 to that power, so I get an x squared. That 5 isn't going anywhere. And then divide by that new power. Divide the whole thing by 2. And then 1, it's important to remember, the same as differentiation, that this 1 is essentially a 1 times x to the 0, because x to the 0 is just 1. So whenever we've got a constant, we can just imagine that there is a secret x to the power of 0 in there. In which case, we will add 1 to that power, so I get x to the power of 1, and then I will divide by my new power, divide by 1, and I can just, get rid of that 1, get rid of that 1, and I just have x. And again, it's always good just to be able to work backwards, differentiate this, and make sure we're correct. So if I differentiate this, times this whole thing by 3, the 3 and the 3 will cancel, 2x minus 1 from the power squared, plus 2 times everything, that becomes 10 over 2, which is 5, x to the power of 2 minus 1 is 1, plus, and hopefully we know at this point the derivative of x is just 1, get rid of the unnecessary 1, I end up where I started and I've got an integration. Good evening. I've made a severe and continuous lapse in my mathematical judgment. Early this evening, I recorded a video entitled Indefinite Integration, a video that you are currently watching, and in it I made a simply unforgivable error. I did something that I berate my students for doing on a daily basis. I forgot to plus C. So let me explain what I mean by that, and you can decide if this is an educational lesson or an actual mistake later. I got to this point in the video, and if I've edited it correctly, which I probably haven't, you should also be at this stage of the video, where I've got a 2x squared plus 5x plus 1, and I've successfully integrated it into 2x cubed over 3 plus 5x squared over 2 plus x. But this is not the entire story. I require a rather nifty little thing called a plus C. Let me explain. Let me take you back to our original equation here. And we know that to get from my blue, my new equation, to the red one, I need to differentiate. But in differentiation, something happens when you have just a number. Imagine this equation here is the same thing but a plus 6. If I differentiate this equation, well, that will turn into that goes up into that, the x turns into a 1. What happens to the 6? Well, the 6 disappears. It becomes nothing. So there won't be a 6. What if there was a 16? Well, there still wouldn't be anything. The derivative of 16 is 0. It'd be plus 0. It'd be nothing. What if it was 167? What if it was 167,000? What if it was 167 over 325? 0.4. It's always going to be 0. The point I'm making is I can add any number to an integral, and when I differentiate it, I will still get the same result. And because of that, I need to add a continuity. I need to add something that says There could be, and there probably is, another number involved here. I just don't know what it is yet. Now, we will see examples of how to find that a bit later on, but for now, we just need to leave it as a C. Once again, I sincerely apologize, and hopefully none of you make the same mistake I did, and you always remember your plus C's. So last thing then, what does this mean? Indefinite integration. Well, lucky for us, there's two forms of integration, indefinite and definite. And the way that I would kind of explain this, again, I'm going to use allegories to differentiation because that's what we're familiar with at this point. Again, let's say I've just got a 3x cubed graph, nothing too crazy. I differentiate that and I get 9x squared. This gives me the gradient of the graph, but it doesn't tell me the gradient of a specific point, right? I still need to put in an x. It just tells me the general, what is the gradient at any point on this graph. And because of that, I would consider this indefinite. We have an expression that tells us theoretically what the gradient is, but without knowing where on the graph I'm looking, it's useless because this graph could have a gradient of all sorts wherever I look. So I would consider this an indefinite differentiation, which is a sentence I've never heard before. So the same logic applies to integration. Here, my integral here, the green one, I have got the equation for the area under this curve. But where? Because this curve here, this quadratic, squeeze it up here. So it's positive quadratic. I'm not going to worry about where anything is. Let's just say it looks like that. Well, this goes on forever. Even though it looks like it goes straight up, these go on forever and ever and ever. So where am I getting the area from? Is it here to here and finding that? Is it here to here and finding that? Well, this is why it's indefinite integration. We don't know yet. We just have the equation that gives us the ability to find the area under the curve. And for that reason, it is indefinite. In the next video, we will look at definite integration and how to turn this into an actual value with an actual area.